All right. Well, who remembers what we were talking about?
Internal loads.
Yeah, internal loads. We're starting to talk about internal loads. And I started with this really simple structure. So from last time, not a structure, just a beam. And normally you would have joints on the beam and you'd have to calculate what the reactions were. But in this case, that was all done before I started. So I had a 500 Newton force like that, a 1000 at the middle, and a 500 like that. And what we did last time was we calculated the internal loads halfway between the left 500 and the 1000. Okay. Well, you would prefer not to, how many points would you have to calculate the internal loads at to represent the whole beam? Infinitely many. So that's going to take a long time, So what you would prefer to do is represent those internal loads as some kind of function as you move along the beam. Okay? So we calculated internal loads at one location along the beam. And we did that by isolating, like the piece that we isolated was everything from the left end up to the point that we were interested in. Remember that? What we'd like to do now is calculate internal loads as a function of the location along the beam. And if we call this our sort of 0x, then positive x goes that way. Okay, so what we are eventually going to get to is calculating the internal loads as a function of x. Okay, to do that, you have to notice this. Okay, so I'm going to isolate, I'm going to draw free body diagrams of 4 pieces of this beam. Okay, so we're going to calculate the internal loads here. That's the first spot we're going to do. The second spot we're going to do is here. Then we're going to do one just on the other side of the 1000. So there's the third one. And then we're going to do one just before the 500. Okay, so I'm going to draw those free body diagrams. So here are the free body diagrams for calculating the internal loads at 1 and 2. Okay, so first free body diagram for calculating the internal loads at 1. So this is a point just a tiny amount to the right of the end point. Okay. So There's the piece we're isolating. Here's all the stuff that we're skipping. Let me put that in this color. Okay. And I'll put the loads on here that we're skipping also. So this 1,000, that's not acting on what we're isolating. This 500 isn't acting on what we're isolating. There is a 500 this way at this location. And then what other loads are acting on that little black piece?
The weld joint.
Yep, the weld joint. And remember, we gave that funny sign convention, funny new names to deal with the sort of ambiguity about whether you're working from the left or the right. Remember that? That was what I was saying. Yeah, when you guys were thinking about MEA weekend or whatever. I like this song. But okay, so what we have now is a fixed joint, a weld joint, right? That's between what we're isolating and the rest of the body. You could just treat it like a regular weld joint. The sort of problem with that is then you don't have a defined set of values for internal loads, because if we calculated the internal loads at that line, remember this is the line that where we're trying to calculate these internal loads. If instead of isolating that little sliver, we isolated all the light blue stuff, we have a Newton's third law pair of things, so everything would be reversed. Okay? Well, what we'd like to do is have just a sign convention that's going to give us the same internal loads at a single point, no matter how we calculate it. So what we did is come up with this new sign convention. There's no reason we had to make it as wacky as we did, but, other people got here before us and messed it up, So we have this new sign convention that does these specific weld joints like this. An internal tension like that, a shear force like that, and a bending moment like that. If we worked from the other side, all three of those loads would be backwards. That's how the sign convention works. And then you'd get the exact same values for it no matter how you calculate it. Okay, so that's the benefit of this. Okay, so there's our free body diagram for that. That's for this little sliver. Now let's draw a free body diagram at 2. So now say we want to calculate the internal loads at that point 2. And that looks like this. We still haven't, this time we've almost gotten to the 1,000 up, but still not quite. We're still not at this 500. We still have the 500 here. And we still have the weld joint here, the internal loads, T, V, and M. And so look at those two free body diagrams and notice that they have a qualitative similarity, So notice these two FBDs are really the same, except for the length of material we're considering. So instead of doing these as two separate things, yes?
Is there a reason why on the second free body the 500 is going up?
The second? No, that's a mistake. I mean, there is a reason. It's that I did it wrong. Thank you. Okay, so instead of drawing separate free body diagrams and doing separate calculations for those two things, okay, watch this. This is going to be awesome. So we're going to go a free body diagram where I just choose some arbitrary amount of that material in between those two lengths, you know. I'm still skipping all this. We have the 500 down. T, V, and M. And then, well, what's the length of that? Because this is supposed to represent two different lengths, and really anything in between two. Well, just call this X. So we'll just say that this distance is X. Okay, and now to calculate the internal loads. First is Newton's second law. It says 0, negative 500, plus this t is in the positive x direction, so that's t0. V is in the negative y direction, so that's 0, negative v. That's all the loads. It's in static equilibrium, so that's all equal to 0. And so from this, we can see that t is equal to 0 and v is equal to negative 500. And those loads are totally independent of what the length of material is you're considering between something just between a line just past the left end to a line just before the first load there. Okay? Now let's do the moment equation. All right, well, this is going to be my about point. Always, this is going to be my about point, so just get used to using that. All right, so that 500, does that produce a moment around that about point? No. Does the t produce a moment? No. M is just a couple, so we have M. Then what's the moment produced by that shear force V? This is the one thing that where this X comes into play. So notice that we have plus or minus a force of V times a moment arm of X. Okay? That's everything that produces moments. Does that V cause a clockwise or counterclockwise rotation around that about point? Clockwise, so we want the negative. And so this equation says M is equal to Vx. We already know V is negative 500. So M is equal to negative 500x. And those are the internal loads. Okay, so now these are functions of x. Okay, well, we've considered the internal loads, like this works for any x values between that 0.1 and that 0.2, okay? So let's see what happens if we go to the points 3 and 4, okay? So now consider the internal loads at 3 and 4. A free body diagram for that point 3 we're not going all the way to the end, so that doesn't appear in our body. But we are going far enough that our free body now includes this 1,000. Okay? We still have the 500. We still have the internal loads, P, V, and M. So what are these distances? Well, the distance to that 1,000 Newton force, I didn't give the length of this, but we had it last time. What did I think I said the whole thing was 1 meter. So that 1,000 is half a meter. Yeah.
So our x from free body diagrams 1 and 2, that's from just inside of 1 to just to the left.
Yes, and that's going to be a really important point, because what we're going to see right now is that when with these two new places, we want the internal loads, even though, 3 and 4 are, 2 and 3 are, you can think of it as like infinitesimally close to each other. The fact that that 1,000 is in between them means that this free body diagram is not going to look qualitatively like those other two. So something important changes when you hit those point loads.
So even when we move to 3 and 4, x is still staying the same distance, not changing.
Well, so x is going to mean, so in this case, x meant something between, meant anything between a little more than 0 to a little less than 0.5. Now, in the new set, x is going to mean something between a little more than 0.5 to a little less than 1, and anything in between. Okay, so what's the distance between the left end and the 1,000 Newton force? 0.5, yep, and that doesn't change. No matter, we'll see that in when we draw free body diagram 4 also. But this distance is still going to be x. Okay, so Newton's second law says 0, negative 500 plus 0, 1,000 plus T0 plus 0, negative V is equal to zeros. And so T is still equal to 0. V is now equal to positive 500. And now we'll go to the moment equation. And so if this is our about point, what do we have for moments? That 1,000 produces a moment. So that's plus or minus 1,000 times its moment arm of 0.5. Would that cause a clockwise or counterclockwise rotation? Counter, so this is positive. Then we have the plus m like we had before, and the minus Vx like we had before. Because that V has a moment arm of X and would make it rotate clockwise. Okay, so this is equal to 0, and we get that M is equal to Vx minus 500. V is 500 now for these X values. And so M is equal to 500 X minus 500. And let's do the same thing for 4. So this time we're almost including the whole thing. We're leaving off this much. That means that we're leaving off that 500 at the right end. But we do have the 500 at the left end. We do have the 1,000 at the middle. And we do have the internal loads. And what are the distances? This distance is still 0.5. And this distance is X. Okay? And so if you go through this, you get the same thing we did before, ... T is 0, V is 500, M is 500, X minus 500. Okay, so let me say the free body diagrams. The free body diagrams for 1 and 2 are, I mean, the distances aren't the same, but they're qualitatively the same. The ones for 3 and 4 are also qualitatively the same. So now we sort of see a strategy, okay? First, identify the points where a point load is applied or we'll also see that we want to figure out where any distributed load functions change. Okay. This is going to give you, let's say that this is going to give you n points. Second, draw a free body diagram and calculate the general internal loads for x values between the points that you identified we're going to call these the cuts. And so how many cuts are we going to have in general?
-1.
Perfect. N minus 1. Okay. And then the final thing is give the internal loads as piecewise functions of x. Okay. So for the example above, our internal tension, like what's the tension in that beam? Well, for x values, where did I start that? 1, 2. For x values between x equals 0 and x equals 0.5, we add a t of 0. Okay. And for x values between an x of 0.5 and 1, we also add a t equals 0. So, okay, this is a warm-up one. T, as a function of x, is just equal to 0. It doesn't have any internal tension anywhere. Okay? What about the shear force as a function of x? Well, that did change. For x's between 0 and 0.5, we had negative 500. And that's for x's in the range from 0 to 0.5. Does that include the endpoints, the way we did this calculation? It doesn't. You can see that in the way that I chose those free body diagrams. I chose those points just a little bit off of where those loads are applied. Okay, so and then it switched to positive 500 for x's in the range from 0.5 to 1. And then the bending moment. Well, these are the only one in this simple case where we had explicitly functions of x, so for x from go away. For x's between 0 and 0.5, we had this function negative 500x. For x's between 0.5 and 1, we had 500x minus 500. And there it is. We've mathematically represented the internal loads for this whole beam based on the x value, so if you want to know now what the internal load is 0.75 from the left end of the beam, just plug 0.75 into your x value, your x function, and it'll give you the answer. Okay? Anybody have any questions about what we're doing and why? Okay.
Can you do this not for beams, but like in a plane or in 3D?
No. But we can, if you have symmetry, like if you think of this as, okay, so if you think of this thing being a plate where everything's symmetrical in your line of sight, then yes, you can do it this way. But remember that we're not calculating internal load. A lot of times I'm saying calculated at this point. We're really calculating it. Notice if this has a finite thickness, we're calculating loads along a line. And if you think of that as having dimensions into the page, you're also calculating it into the page. So what you're really calculating are like internal loads along a plane, if you can imagine, like slices in this thing. And yeah, you could do that, but it doesn't have any real utility beyond like just a beam. Okay. When we get into mechanics of materials next semester or whatever, whenever you take that class, we're going to go from this calculation that's along kind of a plane into figuring out how that represents stresses and strains at individual points on that plane. So far, we are getting more specific than we've gotten in the past about calculating external loads, but we're not breaking it down to like individual points yet. Okay. Well, if you want to visualize what's going on, you could graph these. That would be sort of an obvious thing to do, So let's think about what these look like. So the tension as a function of x, let's say that this is the point 1. It's just 0 the whole way. The shear force, so here's 0.5, here's 1. There's negative 500, positive 500, and it looks like this. What about that one point? Like if this was a math class, you would draw a circle here. You don't know what that value is. You draw circles at the two endpoints because we have these 3 spots where we haven't done any calculation. But remember that point loads are really kind of mathematical. They're kind of made up things anyways. Everything's distributed over at least some distance. And so we're going to sort of just gloss over that fact and just connect these like this. If it was a distributed load, what would that look like? Well, it would just look like a diagonal line. It would just be very steep, So we don't really know what's going on exactly at that point, but this gives us as much information as we want. And then the last one, the only one that takes any thinking on this for graphing. So there's 0.5, there's 1. These are linear functions, right? These two functions are linear. At x equals 0, we're at 0. At x equals 0.5, we're leading up to a point of negative 250 Newton meters. And then this one, if x is equal to 0.5, this starts at the same point this one ended at, and it goes to 0. So this looks like this piecewise linear function like that. Anyone have any sense how many Newton meters of torque you can apply with, say, like a screwdriver, like with your hand? I mean, just to put it, to compare to 250 Newton meters. Anyone have a feel for that? I don't know, somewhere in the 10 range, maybe, if you're really twisting a screwdriver hard, So that gives you a little sense of how big that is. Anybody have any questions about that? Okay, so things are going to get more complicated when we have distributed loads, as you can imagine. But let's just do a full example, just go through the method that I just kind of outlined. So let's say we have a pin joint over here, a roller at the middle, and let's say that there's a force pushing this way at the midpoint of 1,000 newtons, a force pushing this way of 600 newtons, and a downward force of 2,000 newtons.
I missed what the corner is there.
This is a pin joint.
No, sorry, the arrow that like.
Oh.
90.
That's just because it would be messy if I wrote that vector along the line. So that's just saying this is 1,000 Newton force going to the left, located at the middle. That's all that means.
Okay, it has nothing to do with the roller.
Right. It's just at the location of the roller. Okay, so the first thing you have to do is calculate the external loads. Notice that, like in that simple example, I just went through a bunch of different ways. That had already been done for you. I just gave you the free body diagram, but we're going to have to start by calculating the external loads. So free body diagram. Oh, that was hideous. Okay. At the pin, we're going to always assume these have no thickness. So that's just not something you have to worry about. It doesn't make it any harder if you deal with the thickness. But so I'll call this RA. That's the force vector applied by the pin. Then at the roller, I'll call that RB. We know the direction of that. And we have the 1,000 Newton force there. And then 600 there. And 2,000 there. So Newton's second law says RAX, RAY plus 0 RB plus negative 1,000 0 plus, I don't know, these are both at the same point. I'll just make that a single force vector of positive 600, negative 2,000. Is equal to zeros. So we got RAX is equal to positive 400. We can't calculate the y component yet, so now let's go to the moment equation. And I'll put my about point here. Does the 1,000 Newton force produce a moment? I mean, it's a little hard to tell maybe if you're not used to that notation, but that 1,000 Newton force is just acting right along the long axis of the beam. So that doesn't produce a moment. The RB does. Oh, I didn't give any lengths. Let's say this is 1 meter and this is 1 meter. Okay, so that RB, so plus or minus a moment arm of 1 times the force RB, would that rotate it clockwise or counterclockwise around the about point? Counter, so positive. Does the 600 produce a moment? No. The 2,000? Yeah. Plus or minus. The moment arm is 2. The force is 2,000. Is that clockwise or counterclockwise? Clockwise, so this is negative. So RB minus 4,000 is equal to 0. So RB is equal to 4,000. And so now plug that into the y equation, and you get RA is negative 2,000. So, okay, we get RA is 400, negative 2,000. RB is 4,000. Okay. And any questions about that? So now we can go to our cuts. Now we're into the internal loads calculation. So how many cuts are there going to be for this one? There's going to be, so what's our n value? Like how many points are there where you have either point forces or a change in the distributed load?
3.
3. And so we're going to have 2 cuts.
What if you have no forces on the end? On the ends?
Yeah, I guess you still have to, yeah. Okay, sure.
Your first example, you just did extra points just to show that they're the same.
Endpoints also. That's point C. Okay. So cut 1. This is going to be for X values between 0 and 1 meter. I'm going to stop drawing the light blue stuff that we skipped now. So what do we have there? Well, we have that RA force because we're always going all the way from the left to our X value. So our RA is 400, negative 2,000. We haven't gotten to the roller or the 1,000 yet. So the only other thing we have is T, V, and M. So Newton's second law says 400, negative 2,000 plus T0 plus 0 negative v is equal to zeros. And so t is equal to negative 400. And v is equal to negative 2,000. Is this beam in compression or tension on the first half? Compression, that's right. So if you have a negative t value, it means it's in compression. And then the moment equation, I'm always going to choose the left end as my about point. So there's, I mean, you'd get the same answers if you did it another way, but just keep doing it the same way. No moments for these, nothing for the t. So you just have m minus vx is equal to 0. So m is equal to vx. V is negative 2,000. So this. Any questions about cut 1?
Can we go through the rotational Newton's second law?
Yeah. No moments for that about point for the forces at the left. T, the line of action goes through the about point, so nothing for T. Then you add on the couple.
Yep.
And then this thing has a length of x, so its moment arm is x. The force is v. It's a clockwise rotation, so it's negative.
M minus V or X.
Yep. And you'll always have m minus vx added to your other stuff because of those two.
Okay, and then we're using our value we found for V,
Right.
and that's how we're getting our equation
Yes,
right away.
that's right.
Okay.
That's right. So that's the thing, is that this is your v. And then cut 2. This is valid for, okay, so these functions that we got, remember, are for x's between 0 and 1 only. So these functions don't mean anything if you're outside of those x values. This is a piecewise function. Okay. So now cut 2 is for x values between 1 and 2. So we have 400, negative 2,000. At the midpoint of the whole beam, we have 4,000. Like, notice that's not the midpoint of our piece. That's the midpoint of the whole beam. And we also have a horizontal force this way of, what was that? 1,000. I'm just going off of, so now our, the piece that we're cutting has to include those two things happening at the midpoint, which are that 1,000 Newton horizontal force and that RB that now we know the value of from the statics. And then we have the internal loads. So Newton's second law says 400, negative 2,000, plus negative 1,000, positive 4,000, plus T0, plus 0, negative V.
Can we just combine the T and V in one vector?
Yeah. Yep. And you get T is equal to positive 600. V is equal to positive 2,000. And the moment equation, nothing for the stuff on the left, nothing for the 1,000. We do have a moment arm of 1 and a force of 4,000. Is that clockwise or counterclockwise? Counter. So that's positive plus m minus Vx is equal to 0. And so m is equal to 2,000x minus 4,000. And so if you draw these diagrams again, for the internal tension, you go minus 400, positive 600, for the shear force, you go negative 2,000, positive 2,000. And for the bending moment, it comes down to negative 2,000 and looks like that. Any questions about that?
Why do we only include one endpoint for calculating the internal loads on these graphs? Why not like that? Why not the 500 or whatever it was? Right side.
Right. Well, it is included in those calculations because it came into the external load calculations.
Oh, okay.
But
Gotcha.
like I said, because we use this sort of funny new sign convention, we could do all this stuff working from right to left, and then we wouldn't explicitly take into account the stuff happening at the left, and we'd get all the same answers.
Gotcha. Okay. That makes sense.
Okay, that's all.